data removal, sometimes let's say there is one attribute that is missing in many rows. So of course, if you have to remove all those rows, then you're going to have a problem with the data. It's better to remove that column, right? So that's a fundamental thing. But other than that, if you have kind of more missing attributes for some data points, right, then it makes sense to remove those data points. And then, of course, we can do other things like random sampling or informative sampling, right? Informative sampling is related to this idea of something called active learning, right? So when we have a data set, I'm now showing the data set as a space, right? So we have data all over like this, right? Now, if we take data from a certain part of this space, right, we may not be having a very representative data set. So how do we take the most representative data set? Normally in statistics, we do this by random sampling, but we can use knowledge of the data to do something called active learning, which is trying to extract the most informative data samples. Right. And a third thing which people don't talk too much about is how to integrate heterogeneous data sources. You may have some data sets as tables like this, some as strings or text, and some in a network structure. We are not going to really talk about this because there are no general techniques to do this, but there are some general principles. And the task 3 is prediction, right? And one type of prediction is regression, right? It's an example of supervised learning where we have data and we have the answers, which may be either labels, normally we call it labels if it is classification, or numbers, right? So this predicting the numerical value is regression, predicting a class is classification. So and this is obviously very familiar to you, so that's why I said today we are just doing like some things that you already know about. This data set shows the input data and a label, a class label, or a numeric label. If it's numeric, we say regression. And in regression, we are basically, simplest case is we have the target variable and one independent variable, right? And we are trying to fit a line. Right? In classification, it's different. We are trying to not fit a line, but we are trying to draw a line that separates the data. Right? So these are the data points, and we are trying to find a line that separates. Right? So, and in all these are the simplest cases. In the case of regression, that was where you have one feature. In classification, this is where you have just sorry, not one feature. Yeah, in regression example, you have one feature and the response variable or the target variable. In classification, we have this simplest case is where we have two features, right? One on the x-axis, one on the y-axis. and we can identify a line that separates two classes. Okay, so the types of learning, right? Building a model consists of learning or training. Right? So we saw in classification, we learn a separator. In regression, we learn a trend line. You can think of clustering also as a type of learning where we learn to structure the data. Right? So this tries to show all the things that we did to now. So a simple regression line, we say something like, y equals mx plus c, or more formally we say y equals beta 0 plus beta 1x, right? And so that you can extend it very easily to y equals beta 0 plus beta 1x1 plus beta 2x2. If you have another variable in the z-axis, beta 3x3 that you can't draw, beta 4x4, that means, if you have more and more features, you have more and more coefficients in a regression task. The general setup is like this, right? So some data you use for learning, another set you leave for testing. Right? So the first question is, why do you do this? Right? Why do this? Can someone give? By the way, there's no right answer. Can anyone tell us why you do this? Separate these two.
To see how well the model performs on unseen data?
Yeah. So in general, what we want to do is we want to build a model. So we can use the whole data set and build a model. And then what we are really going to do is to deploy it, right? We are going to deploy, we are going to use it. When we deploy it, we have no idea how it will perform. So when we train on the whole data set, okay, we get a certain accuracy, so we are happy, and then we go and happily deploy it, right? But we have no idea, except by trial and error, to see how good that model is. And so that's why we do this. And because of that, we can't like take the first part for training and the last part for testing, right? We've got to do it randomly. We have to extract the test data randomly from the whole data set. Now, it's always good to say, okay, is that valid? So if you think about a problem that has seasonality, right? Or where time is an important factor. Basically, that's the key thing. Time is an important factor. Now here, when we take this data set, we remove time from the equation, right? It's just one data set. So then taking randomly is okay. But if time is an important factor, taking randomly may not be a solution, right? May not be representative. Right? I just want you to think about that only. Right? In virtually all cases of supervised learning, we have this assumption that time is not significant. There is no seasonality in the data and so on. Right? Or else we have to capture time into a variable, one of the attributes. Now, then we also typically from this set. Okay, so let's say this is another common thing. So you say, right, I take this data, train and test on this, and I get a value, and I say, well, that's not really good. So I need to try a different model. What are the things I can change? I can change my data cleaning, right, wrangling that part. I can change my feature selection, that part. I can also change my algorithm. Right? Those are the three things you can change. And you keep changing those and testing on this data set. Is there any problem with that? After all, the test data is telling me this is what is going to be the result when you deploy it. So I'm not happy. So I think, okay, there's a problem with my data, or there's a problem with my features, or there's a problem with my algorithm. So I keep trying different algorithms and different data, data cleaning and different feature selections. Is there a problem with that? I mean, you can say there's no problem. That's, there's only a binary answer to my question. So,
there is a problem, sir, because the observation could be owing to something wrong in the distribution of the test set, because we are only dependent on a single test set.
okay. So when we do that, right? If you think about it a bit, when we do that, we are trying to optimize on this testing set. Right? So we may end up tuning our model to precisely this data set, this testing data set. So indirectly, we are training on our testing data. And that's the cardinal sin of machine learning. Right? You never test, you never train on your testing data. Right? But indirectly, if we do this, we are training on our testing data. So that's why we take some portion of this unseen data and we call it a validation set. And we use it for model tuning. By the way, some people call this the validation set. Right? So we train using this part, and we try to get an idea how good our model is, and we keep training our, this is model parameter. When we do hyperparameter tuning, that's what we do here. But it can also train, you can also change your data cleaning, wrangling part, or you can change your feature selection, feature extraction part, or you can also change your modeling algorithm, right? So after you are happy with, okay, this seems to be a good model, then you do this. I mean, it's like, so obviously from all the models you get here, you're going to select the best one. Right? You're going to deploy the best one, right? Unless you decide, okay, I don't have enough data, right? So I'm going to deploy the best one. Just before deploying the best one, I just want to have an idea, right? How it's going to perform. So this is only going to give me an idea, right? And so I only do it just before deploying. I hope that's clear. So when we train a model, okay, this is like showing what happens, right? So in a case of a linear, in the case of regression, right? So these are points and I want to fit a curve. And one way is to fit a line, and you can fit different lines. And then how do you figure out which is the best? Well, you simply look at the distance from your model, which is a function here, to the real value, right? And you add up all those square distances. That's usually called the sum of square errors, right? So you can see here the errors are these dotted lines. Here the errors are less because the dotted lines are less. Here there are no dotted lines, it means perfect fit, right? So which is the best model? Which would you like better? FA, FB, or FC? Well, these are mathematical functions, but we can say MA, model A, model B, model C. If we blindly look at the sum of squared errors in the case of, or the mean squared error, that's the common metric for regression problems, right? If we blindly look at mean square error, this is going to be the model C, right? Model C, almost zero errors or very small errors compared to model A and B, right? But the big problem here is that we are not, so this is the general behavior of these models, right? As the learning progresses, right, we fit more and more complex models, the training error will come down. So, in fact, if you think about clustering, what is called the sum of squared errors is minimum or zero when each data point is in its own cluster, right? So that doesn't give us any benefit, right? So if you look at these three models, right, the error of model A is somewhere in this region, error of model B is somewhere in this region, and error of model C is somewhere in this region, right? And the big problem is, though the model C looks the best, when you take some test data, you see that there is a huge error, right? So that's why we use the test set, right? When the test set comes, it's giving a big error. So one clue that and this is of course typically called overtraining or overfitting, right? One clue for overfitting is the big discrepancy between the training error and the testing error, right? Which basically means the generalization hasn't happened. And good models are models that generalize well. So when you come to the second model, even though there was a higher error, when the new data comes, the test data, there the error is less. So in general, you may have seen this thing as we make the learning process more and more complex, right? The error may keep coming down for the training set up to very low amounts, but the validation error will start rising at some point. So obviously we know that the best point is somewhere here, and we stop training. Right? This is particularly important when we use an algorithm like that application in, and we will see this in deep learning a lot. Right. Right. There is another strategy that we can use, and particularly when the amount of data points are limited, and we find it difficult to keep out some data for testing, and that is cross-validation, where we divide the data set into equal parts and train and test repeatedly by keeping one of those parts for testing, right? So 5 or 10-fold cross-validation is very common, and then we get an average of, so that we get an idea of what is the accuracy of the model. So it's another way of figuring out, right? When we deploy this, what kind of accuracy are we going to get? This is showing it graphically, but not important. Right. So learning types, we've already talked about this. So we have supervised learning when we have the target, unsupervised learning when we don't have the target. There's also semi-supervised learning, right? when we have a little data with the labels. Right? In fact, when you have a little data with the labels, we can do two things. One is you can do clustering with the full data set, and then you can see how the data points with the labels fall into the cluster, right? So if the data points with the labels fall into the different clusters in a way that corresponds to the labels, then we are happier, right? So there are two metrics to measure this, I think, and I may talk about it at the end. Another is, of course, you use this to bootstrap, right? So I take the few that are labeled, and then I try to bootstrap. That means add more and more, label more and more data points, right? And these are both very practical situations. Reinforcement learning, I'm not sure that you've done this. So this is where we don't have the answers, nor do we not have the answers, but we have kind of hints, right? We are not told this is the right answer, but we are told this is the right area. And I don't know how many of you have played this game where we hide some object, like when we were kids, we hide some object and we tell there's one person who doesn't know, and that person then comes into the room and then searches, and then we say hot or cold, right? Hot means you're close to the object that you have to guess. Cold means you are, and it doesn't have to be an object in the room, of course, it can also be an imaginary object. So when every time the person guesses, we say hot or cold to show how close or far we are. So reinforcement learning is a bit like that. But we are not looking at those two here. Yeah, these are just more graphical things. I'm not going to talk about those, right? Finally, models. Yes, you have seen in scikit-learn, I guess you came across several choices for models, right? Linear regression. Logistic regression is actually a classification technique, right? Naive Bayes, and many of these you will see the examples for binary classification, but all of them are extended to multi-class classification. Okay, maybe I don't talk really about multi-label classification here. K nearest neighbor, right? This K is very different to the K means, right? K nearest neighbor means how many neighboring data points do I use to determine the value or the class of a given data point. So the term nearest neighbor should give you an idea that it's about, K is about how many are close to you. Whereas K means is about how many classes or clusters. That K is the how many classes or clusters. This K is about how many neighboring points are close to you. SVM, okay, one time, one of the things that came closest to a universal learning algorithm, right? But now we know there's a thing called no free lunch theorem, right? But at one point this was, and then at a later point this became stochastic gradient descent, and particularly its application to things like boosting, right? Neural networks. These are, we will now call these shallow neural networks, or or multi-layer perceptrons they were called earlier. And then ensemble methods where you combine, and the two common ways of combining are bagging and boosting. And so some of these techniques also became almost like universal algorithms. So the most famous bagging algorithm is a random forest. Right? It's a bootstrap aggregation of decision trees. Right? And so bagging and boosting, if you feel that you don't have a good handle of ensemble, please respond in the discussion thread and we can kind of discuss that a bit, right? The difference between bagging and boosting. So random forest is not the only way to do bootstrap aggregation or bagging, but it's the most common algorithm, right? And boosting again is gradient boosted trees are a way of explaining boosting to show, especially to contrast bagging and boosting. But probably the most famous algorithm came closest to a universal algorithm is XGBoost, extreme gradient boosting. Right. So some people, and that's what you shouldn't do, right? You shouldn't, since you know the no free lunch theorem, you should not say, okay, whatever the data set, I just put XGBoost and I will get the best. It doesn't say so. Sometimes the simplest model like naive Bayes or logistic regression gives you as good and an explainable, right? Some of these models are explainable, and recently explainable AI has become really hot, right? And so by the time you go into the industry and by the time you establish yourself, if a model is not explainable, like and most neural network based models are not explainable, or SVMs are also difficult to explain, right? You will, it will be very hard to convince your top management to use them, right? And so since you are trying to acquire a holistic understanding of all technologies, you should then say, right, maybe my decision tree gets slightly lower than my random forest or XGBoost, or my logistic regression or naive Bayes is giving, but I can explain that. I can explain it better. So let me employ that one. It's having a few percentage points less accuracy. And then, of course, deep learning. And this is basically not an algorithm, right? It's neural networks with lots of hidden layers. And since that is not in general practical, not because of compute power, but because of a problem called the vanishing gradient. We can discuss this if you want, if you raise these things up in the discussion group, right? By the way, I noticed that there's absolutely nothing in the discussion groups, but I hope to leave enough gaps in what I say so that there will be some questions, some comments, and some interaction on the discussion group for this section. I'll have just one discussion group on this analytics section, business analytics. So convolutional neural networks where the spatial distribution is significant, like in images, and recurrent neural networks where the order or significance is important, like in text, or time-related questions like stock market or something. And generally, we don't have the simple vanilla RNN units, but those units are either GRU or more commonly LSTM. And I think some of you may have now come across very powerful models for deep learning for certain tasks called transformers. Right. So, by the way, please read no free lunch theorem online. I don't know, there should be at least a Wikipedia page on it. Right? In unsupervised, we have another set of algorithms for clustering, right? Very often dimensionality reduction is also considered as unsupervised learning, right? So those are the two main unsupervised learning things. So dimensionality reduction is mostly for either visualizing the data or for feature selection, feature selection or feature extraction. Clustering is to have to structure the data. Right? So here you can see K-means, probably the most frequent and popular algorithm because it's highly scalable for very large data sets. Some of these are very, very expensive. Affinity propagation, mean shift, spectral clustering. The second most used clustering is hierarchical, and the so-called agglomerative. You can either have agglomerative or divisive, but agglomerative is more well-known, and Ward's algorithm, for instance. And then there are things where the density is what determines the clusters, right? So density-based models. Some of these are called distribution-based models. And then there are also neural network models like the self-organizing map. Right. This is just one slide, right? Because it's time up. I said I'll finish in 90 minutes every day, but I'm going a little above that. Right? So fraud detection is a type of anomaly detection, right? Because frauds are rare. Right? So the techniques for fraud detection is a little different to standard classification, because the examples you have of fraud are small compared to the normal data. Churn prevention, well, this can be a typical classification problem. You have lots of, you can either have customer churn, right? So somebody is going to leave your product or your supermarket or whatever, right? And can you pick up the signals early enough? Employee churn prediction is, of course, something that employers will be using on you, right? As you join your first workplace, right? They will try to figure out who's the next guy who's going to switch. Churn means, of course, switch, right? So you can switch loyalty if you're a customer to another brand or another supermarket or whatever, or another service provider, or you can switch your workplace, right? So people are trying to pick up the features that predict this, right? And then make interventions. The whole point is to make interventions. So if a customer is about to churn, right, you send them a promotion and blah, blah, and retain. If an employee is about to churn, I don't know, typically not HR, right, but some team lead or someone will be alerted, and then they kind of try to find out if you're unhappy with something. Sentiment analysis, common thing for companies to see the customers' feelings towards their products or services. Recommendation systems, I think we interact daily with these things, whether you're watching, we'll figure out what movie to watch or which book to buy on Amazon or whatever. Right? So network analysis, very often not talked too much about, right? But let's say anything related to, I think probably the most well-known algorithm in this space is Brin and Page. What's it called? You know what Google is based on, right? PageRank. So PageRank has been also used for ranking, I don't know, texts, and then you can imagine you can also rank. We used it to try and rank authors, like publications. Currently, authors are ranked equally, right? Whether you know, whether a school child links to your article or somebody important in at Stanford links to it, you get just one score of one citation, right? But you know, obviously, the guy from Stanford to link to your one, you know, there should be a higher weight, right? So PageRank is one thing to do that with web pages, and you can apply that to lots of areas. So network analysis, and of course in biology and bioinformatics, a lot of that stuff. Predictive maintenance. If you can predict when something is going to break down, right, before it breaks down, because repair is really, really expensive. So cars typically, right, have this built in, so they will give you a lot of alerts through their sensors now. Risk and supply chain management. I think you may have seen some of these things in when you talk about SCM, quality assurance. So how typically batches are rejected based on qualities of not just individual artifacts, but combination of artifacts. Right. So, and there are many more, and I want to take some that are a little unusual, okay, to show you that, you know, these are the usual ones. So yeah, one of the first things, one of the things we will look at is, we will look at some of these also, but we will look at a simple thing like, should I refer? Okay, you're manning a call center, right? And there is a problem that is reported by a caller. Who should you refer these to? It's a common thing that happens in call centers. And currently, it's the caller has the call center operator has to decide that. But can we figure that out ourselves and so on? So you need to be able to figure out, right. There are things that are not typical applications, but I can apply this technology. Right. So here's I normally use the scikit-learn cheat sheet, but this is another cheat sheet I got from somewhere else. It's more comprehensive in the sense it also has reinforcement learning. We are mainly looking at these two, right? So, but it shows that supervised learning can be kind of divided into regression and classification, and these are the kind of applications. These are the kind of applications for classification, and then unsupervised learning into clustering and dimensional reduction. These are kind of things we do with that. And reinforcement learning, you know, used in this kind of application. But we are not really going to look at that. Right. Okay, so I've gone 8 minutes over. I want you to do the first for this week, right? Some tasks, and these tasks are what actually makes you learn, not this lecture session. Right? It's a task. So the task I want you to do is to install RapidMiner. Okay. If you have already used Weka, you know what this is, a graphical tool, but it's obviously much more powerful in terms of business analytics for these tasks. Right? There's a free license that is restricted to 10,000 rows, and I mean, obviously, we are not going to use anything more, right, for this, but you can apply for an unlimited education license. by quoting my class, I don't know if it works yet, right? It used to work in the past years, but I have not been very active on that. And there are lots of help tutorial. There's nice tutorial that is built into RapidMiner as you install and as you run it. So that may itself be enough for you to learn. To do this credit approval example using naive Bayes. And from the next time onwards, I want you to have your laptop open with whatever software running, right? In this case, RapidMiner running. Right? So I'm saying flip classroom mode in operation in the sense that this session is not expected to really be the thing you learn from, but what you do during the week, right? That's another reason why recording this session is not really doesn't make much sense, right? So the slide deck is there for you to just because you have already done all this stuff, right? But it's a different way of saying. Each person will say it in a different way. So this last slide is actually the main thing for this week. I will upload this chapter, and you're going to play around with RapidMiner to implement a classifier to say whether, so typically in a bank, should I approve this credit application or not? This loan application, should I approve or not? It will be the same for a credit card, for instance. Should I decline a credit card thing because it looks a bit fishy, right? It looks a bit of a fraud. Right. So I highly recommend that you try to download this. I don't know, maybe using your nighttime bandwidth tonight, right? And then get familiar with it. I'll just very quickly show you what it looks like, right? A graphical interface, and so here's I read my CSV file. I do some renaming, replacing, so the pre-processing with some filtering some things, and then discretizing the data, and then doing cross-validation. Right? So pipeline, a very, very simple pipeline, a very rich interface, right? So these are all these, it's like a puzzle, right? And each of these components are given here. So you may say, oh, wow, for data access, there are 58, right? For blending, what is that? You don't need to know, but modeling, 167. So obviously, there are lots of algorithms. But you don't have to know all that. You can kind of, let's say, type evaluation, something. And then you get all the things that are there for evaluation. Or you can say a tree or decision, random forest. Right? You can easily come to the random forest very fast like that. Right? To find these boxes. But before that, automatically when you load this the first time, you will find a tutorial that will take you through this interface. Right? And each of these boxes, when you click, you get the attributes you can set. Right? But there's nothing like learning for yourself. So I highly recommend, after you install and blah, blah, a 2-hour session, apart from installing and like going through a tutorial, a 2-hour session to do the credit rating problem, which I will upload. Right now, that text is a bit dated, and so you may not get the exact names of these boxes. Right, so that's another thing, another learning process. Like, okay, cross-validation now. How does cross-validation? There is nothing for cross-validation now. So what's the equivalent thing that is there now? And this help is this search is very important. So even if cross-validation is called something else, now of course it is not called, this example is called exactly the same, but if it was called something else, you still should be able to get the so here you say gradient boosting trees, Bayesian boosting, ADA boost, and so on, right? So, or if you put ensemble, we have random forest gradient boost trees and things like that. Okay, so a minimum of 1 2-hour session, other than the installing and tutorial, right? That may require another 2-hour session, right? But to do the problem, not just to read and just do it mindlessly, but think and do it, I think you will need yet another 2 hours. Now, I know in one of the past years, somebody came, I used to check the next day how long it took. And one particular person came and said, that I took 12 hours to do this week's work. Right? So now I don't want that to happen, right? But I generally judge how effective my session has been, not by how many came and whether they were sleeping or eating or whatever, but how many spent, how long did they spend between this session and next Friday's morning session, right? Doesn't mean that the longest is the best. So 12 hours, I said, okay, I'm very sorry, that was not intended, right? And I changed that particular hand and that particular task because that was too much, right? But if somebody said 1 hour, I know that that person wouldn't have actually finished it or would not have thought about it, right? So that's why I'm giving a rough average. You may need like 2 2-hour sessions to do the work needed during the week. So I highly recommend you, right? So I'm going a bit above today, right? The 90-minute promise. I highly recommend that you try to download during a nighttime or early morning bandwidth if you have, right? And out of those, by the way, I know all of you do the night thing, but my recommendation is go to sleep before 12. Somebody has said 1 hour before 12 is equivalent to 2 hours after 12, right? There is some science to that also. The body needs a chunk of time to regenerate. So why don't you go to sleep early, but get up at 5 or 6, I don't know, 5. You still have 2 or 3 hours of download time in the off peak, right? So that I highly recommend to do early morning tomorrow, right? Or of course, if you happen to be up in the night, then yeah, up. Anyway, off peak bandwidth. It's not very big, but you can save a bit of bandwidth. And then to spend 2 hours setting up, going through the tutorial, that is online tutorial. Online meaning in this interface itself, there is a tutorial, right? To go through that. And another 2-hour session during the week, right? To try to do that problem, for which the what to do and how to do everything is given, right? But there may be some of those are deprecated. I just also thought of showing you another graphical thing. This is called Orange, right? It's packaged in Python, right? So you can see the difference is that these widgets are circular and those are square, right? But the abilities, are different. But having a broad understanding. So you're going a little more in depth in the RapidMiner, but a broad understanding of there are these kinds of tools. K9 is another one, KNIME, right? And we are not going to look at all these. We are just going to use only RapidMiner for graphical, as an example of a graphical tool. Any questions before we finish up? Let me assure you that doing it by yourself, whatever you learn, you will have with you for much longer than whatever I teach in class. So that's the idea of setting this work that will take about 4 hours of your time between now and next Friday morning. Okay, so if there are no questions, we end the session. From next week, definitely it will be 90 minutes maximum. And have a productive weekend.
Thank you, sir.